Bismillahirrahmanirrahim. Assalamu alaikum, people. Morning, people. Afternoon, people. Evening, people. And to all my Muslim brothers and sisters, Assalamu alaikum. Um, we did chapter 2.1 previously, and obviously on chapter 2.1, we spoke about a little bit about the time independent Schrodinger wave equation. We spoke a little bit about, you know, how do you solve the time dependent part, the time independent part. We also spoke about why you can't, we also spoke about like why you cannot solve for why it is not necessary to solve for the time independent part, but you need to focus on the space independent space part and stuff like that. So we spoke a bit. Okay, what is this doing here? I'm sorry, but what is this doing here? Okay, wait, I need to change something. And so today we are going to do chapter. Okay, what is this? Is it stuck onto something? What is it stuck on? Oh, okay. I got it. So the only reason it was stuck onto something was because, let me just delete that. So today we are going to do chapter 2 section 1, which focuses on, okay, what is going on? I don't understand. Or did I minimize it? That's why. Ah, yeah, I minimized it. Now let me test out. Nope. You have to keep that. I told you have to keep that. But can we keep that? Yes. Can we keep that? Yes. Can we keep that? Yes. Good. So we're going to start off with section 2.2. That is the infinite square well. And that is also a mom. I never wrote mom. So that'll also be one of the first steps. Oh, wait. That'll also be one of the first steps of, you finding out the equation for space, as that is also important. So you need to find the equation for space, because finding the equation for time, this is chapter 2.1. So finding the equation for time had no value, remember? So finding the equation for time had no value, and so we need to find the equation for space. And so to make sure that we find the equation for space, this is the first step, right? Make Valentina, Gomez, Noriega, Brown. I always do that. I always do that because it's a ritual now. I think everyone should know by now that why I, you know, love Valentina Gomez, right? Not because, oh, she's, I mean, yes, I mean, first of all, she's elder than me. Think about it. She's elder than me. So there is a very good reason why I love her. Not because she's elder than me, but because she's better than me. All right. So let's begin with our first step. That is the piecewise function. So step one, piecewise function. So obviously you know what book you're using, right? So you're using the Introduction to Quantum Mechanics by David J. Griffiths, the third edition. Make sure that you're specifically using the third edition, because if you use the second edition, some of the equations there are wrong. Some of the equations there are wrong. And third edition is the last book, and it has the updated version. Second edition is the older version, and whatever research has been done, not all the research has been done on that specific time, but now on the third edition you're going to see more updates, so which means you're also going to see more chapters. Cool. Let's begin. So step one, we define the potential. So in your infinite square world, we're going to have this wall. So we're going to have v of x. So v of x is equal to 0 as 0 less than or equal to x less than or equal to a and infinite otherwise. This means that in your wall, can you guys see? So in your wall here, no, we're not trying to solve anything. Okay. So, oh, okay. So in your wall, inside the wall, inside the wall, your v of x is 0. Outside the wall, your v of x is infinite. This means your psi of x here is infinite, psi of x here is 0. Why? Well, no, not why, as in what this means. What this means is that this is not required. We don't have to focus on that. We're only focusing on what is inside the box, right? We're focusing on what is inside the box. Cool. So inside the box, we're going to have your v of x is equal to 0, which means psi of x is infinite. And outside the box, we're going to have v of x being infinite, psi of x being 0. So we don't have to think of that. All right. What does infinite way? No, actually, this is infinite potential. So psi of x, I mean, v of x infinite on the outside. What does this mean? V of x 0 on the inside, v of x infinite outside. What does that mean? When your potential is infinite, so when v of x is infinite, this means the particles cannot exist outside the wall. And you need to give me a few minutes. I smell some burning. So give me a few minutes. All right. So this means the particles cannot exist outside the walls, right? Now, psi of x equals 0 means particles are trapped outside. Because the potential is infinite, it's consider it like gravity. When your gravity is infinite, it's like poof. It cannot do anything. It's like poof. That doesn't mean the particle is at a specific position. Please don't presume that the particle is at a specific position. It's like the particle is poof. It is so heavy, like the gravity outside the wall is so heavy that it is not able to actually jump out, or is not able to, you know, go out or maybe move out, move or whatever. Inside the wall, it can move, like wave, right? So this is why we say that a particle in quantum mechanics, quantum particle behaves like a particle and behaves like a wave. And so inside the um, wall, we find the probability of a particle because the particle can move freely. It can move freely like a wave, and it can also move freely like a particle. Outside the wall, it is so heavy, the gravity of the particle will be so the gravity outside the wall will be so heavy, it's just going to poof, right? It's just going to like stick down and it cannot go up, right? So that's there. And then now we're gonna write the Schrodinger equation. So what do we know about our Schrodinger equation? We know that minus h bar square upon 2m curl square psi by curl x square plus v psi is equal to e psi. Now this is the time independent. Remember why is it time independent? Because initially it is time dependent, but finding the time equation and then implementing the time doesn't help. Because at the end of the day, what do we want? We want to find the space equation. One, that's one. Two, even if we were to find the probability, we have to find the probability density. This is literally probability. This is probability by finding the probability density. And if I do that, the time variant cancels out easily. So typically you have one somewhere, and that one is actually the time variant, because the time variant literally shambled from this one whole equation to just one. So one multiplied the equation is the equation itself, so it doesn't matter, right? So we need to focus on the time independent. So this is our Schrodinger equation. Now we know what? We know that inside the wall, v of x is equal to 0. So now what do we have? We have that'll be d squared psi. You can write curl square psi, but then again, writing the curl, writing the d, it doesn't matter, because at the end of the day, we are only focusing on space. We are not focusing on time. So we don't have to write the partial differentiation, right? We can only focus on the d part rather than the curl part. We have minus h bar square upon 2m d square psi by dx square plus 0 is equal to E psi. And so what we can do is d square psi by dx square is equal to minus 2 by 2m by h bar square E psi. Now, what we did was we multiplied both sides of the equation by 2m by h bar square. And so if I multiply both sides by 2m by h bar square, right, I can cancel out both sides. So I can cancel this out, cancel this out, cancel this out, cancel that out, and I can also cancel the minus out. And if I bring the same multiplication, I will bring the same multiplication here. So then I'm going to have minus 2m by h bar square E psi. Or you write d square psi by dx square is equal to minus 2me by h bar square psi, right? Minus 2me by h bar square psi. Cool. Now we have our second order differentiation equation. Now, if you're lucky, you'll be given this equation on your formula sheet when you do the finals. I was very lucky to be given a formula sheet during my finals. But if you're not given, this will also be open on the, I believe on Calc 3, the trigonometric part. One thing you have to know is that k square is equal to 2me by h bar square. And so this is typically d square psi by dx square is equal to minus k square psi. And so we're going to have psi of x is equal to a sine kx plus b cosine kx. Now, how to solve this? Again, in my case, it was given, so pretty lucky. But if not, I don't know how to solve it. I'm being honest here. I don't know how to solve it, but maybe like in most cases, this should be given as your formula sheet. If not, please find out like how to solve it. But I'm not entirely sure. But this is given on our formula sheet, and we have also done this in calculus 3, the trigonometric part, and vector calculus. We have done this, and in the vector calculus they'll be giving this general equation, and so from that general equation I have to memorize that, right? Now, all right, cool. So we have what? So we have psi of x. We have for x is equal to 0 and x is equal to a. I don't know if you guys can see. So for we have psi of x for x is equal to 0 and x is equal to a. If I do psi of 0, you're going to have a sine 0 plus b cosine 0, right? You're going to have a sine 0 plus b cosine 0. So this will turn as 0. Psi of 0 is 0. So 0 is equal to b cosine 0. So B will just be 0 because that cosine of 0 is equivalent to 1. All right. So B cosine 0 doesn't exist. The cosine angle does not exist. Now we have x is equal to A. We have psi of A is equal to A sine Ka. Right? Psi of A is equal to A sine Ka. So psi of A is equal to A sine Ka. Now psi of A is what? Psi of A is equal to 0. But 0 is equal to A sine Ka. Automatically, you're going to say what? 0 is equal to sine Ka. And so this K will be 0. You cannot have 0 because what I also did was actually kind of wrong. This, I cannot have A is equal to 0. I can't have that because I already know that B is equal to 0. If I have A is equal to 0, this will violate the entire rule for quantum mechanics. This literally violates the entire quantum mechanics rule because none of it can be 0. We can have one of them 0, that is completely fine. But if I have the other thing as 0, what does it tell me? It is deterministic. What is the deterministic part here? That we don't have anything. In quantum mechanics, you will never have nothing. You're always going to have something. And so this is like saying you have a wall here. That's literally it. And obviously, if you were to if you were to do quantum mechanics, you are never going to encounter a time when the wall has nothing in it. It's always going to have something, right? It's always going to have something in it, regardless of what you say. Regardless, it is always going to have something in it. Why it is going to have something in it? Because this is quantum mechanics. You are going to find the probability. You cannot have psi square equals 0. Your psi square is always what? 1, never 0. Psi square is greater than 0. Not greater than or equal to, greater than 0. But psi square is always equivalent to 1. If I have both of them 0, I'm doomed. I cannot have that. However, just because I have 0 is equal to A sine Ka, this sine Ka equals 0, then you're going to say, okay, Ka will be 0. Nope. Just because Ka is 0, like just because you have 0 equals sine Ka, doesn't mean that Ka will not be 0. Ka will not be 0. Because if you look at your wall, if you have one wave, there is 0. There is two waves actually, 0 and pi. This is 0 and 2 pi. This is 0 and 3 pi. You see, at pi it is 0, at 2 pi it is 0, at 3 pi it is 0, at 4 pi it is 0. So what I'm seeing here, I'm seeing that Ka will equal n pi for n is equal to 1, 2, 3, 4, 5, whatever, any discrete integer, any discrete deterministic integer, for any discrete integer n, for any discrete integer n, I can write Ka is equal to 0. So which means my sine 0, sine Ka equals 0 is accepted for any n integer, but I cannot have n is equal to 0. Because if I have n is equal to 0, that does satisfy, yes, that does satisfy, that is good. But n equals 0 means there is no wave. Again, it is violating the entire definition of what quantum mechanics is. right? Because n equals 0 means no wave. But in quantum mechanics, you can never have no wave. You can never have that. It's impossible. It is impossible to have no wave at all. There will be something, because at the end of the day, we're measuring what? We're measuring probability. And to encounter a point where there is nothing, then my psi square just ends up what? My psi square ends up 0, which again, I can't have that, right? Cool. Now, why did we find Ka is equal to n pi? Why Ka is equal to n pi? In a particle, you're always going to have what? Energy. The only reason the particles are able to move both as particles and both as waves is that these two have one thing in common. That is what he called energy. Whether it's a quantum particle, whether it's a classical particle, whether it's anything, there will always be some energy. But how do we calculate the energy level of that specific quantum particle? Now I know that k square is what? 2me by h bar square. And k of n is what? K is what? N pi divided by a, because Ka is equal to n pi and then K is equal to n pi divided by a. So I can write n pi. So I can write n pi divided by a is equal to 2me upon h bar square. So n pi divided by a is equal to 2me divided by h bar square. And what I will do is n pi divided by a is equal to 2m by h bar square e. What I'm going to do next is e is equal to n pi divided by a divided by 2m by h bar square, or I can just multiply, so I can just swap them. You can do little algebra here. Oh, come on. So n pi divided by a times h bar square by 2m. So I wrote that, but it's going to take time. I'm just going to charge some time. So what we did here is, first of all, I'm just going to charge the pencil. So what we did here, first of all, is k is equal to n pi divided by a, and then n pi divided by a is equal to 2me by h bar square. So n pi divided by a is 2m divided by h bar square e, and I need to find the energy equation because I, at the end of the day, need to find the energy level. And so what I'm going to do is E is equal to n pi divided by a divided by 2m by h bar square. Yes, you can multiply, and when you multiply, it's going to swap. So you can do that. So then we're going to have E is equal to n pi h bar square divided by 2ma a square, 2ma square. Why is it a square? Because k square is 2me by h bar square, but k is n pi divided by a. I would have to square that. So which means I'm going to have n square pi square h bar square divided by 2ma square. And this is what will give me the energy level of my quantum particle. For n equals 1, I'm going to get the first energy level. For n equals 2, I'm going to get the second energy level. For n equals 3, I'm going to get the third energy level. N equals 4, fourth energy level, so on and so forth. Until when I reach n, and when I get the n, when I have reach n, then I'm going to get the nth energy level. Cool? Now, what do we know now? Now what do we know? Now we know that psi of x. So psi of x is equal to a sine kx. But what is k now? N pi divided by a, right? So psi of x is equal to a sine n pi divided by a x. Yes, you can write n pi x divided by a. So we're going to have psi of x is equal to a sine n pi x divided by a. And now what I'm going to do is, what do I know about normalization? In my normalization equation, I know that my probability from minus infinite plus infinite psi of x whole square is equal to 1. Wait, wait. I am not going to write minus infinite to plus infinite because my range is from 0 to a. Dx is equal to 1. Now you may ask, why 0 to a? Why not minus infinite to plus infinite? And why 1 for 0 to a? Because first of all, I do not know where, what is the probability that the particle exists on that region. However, one thing I can always confirm by the normalization definition is that inside the wall, the particle must exist. The particle must exist regardless. The particle must exist. Because if the particle does not exist, then you're finished. And because the particle exists, I am certain about it. And because I'm certain about that, the fact that particle exists is going to be 1, indicating that is 100%. Cool? Cool stuff? So we have psi n of x squared dx is equal to 1. What I'm going to do is do the probability, do the substitution of wave function and stuff like that. So I'm going to have 0 a square sine square n pi x by a dx is equal to 1. You can take the constant out. Your constant is the a here. So a square 0 a sine square n pi x divided by a dx is equivalent to 1. And yes, you can also do, so that's just going to be a by 2, right? Sine square n pi x divided by a dx, that's just a by 2. So you're going to have a square a by 2 is equal to 1. So I will have a square is equal to 2 by a, and then 2 upon a, then a will be root of 2 upon a. So now I know my amplitude. So I know that psi n of x is root of 2 by a sine n pi x divided by a, right? The root of 2 by a sine n pi x divided by a. Now, what do we know about the waves? If I draw the waves now, at n equals 1, this is n equals 1, right? This is n equals 1. Actually, I'm just going to draw a bit smaller. Why? Because I have a text above it that I made a vow never to erase it. So this is n equals 1. And because this is n equals 1, what's my highest point here? It is 0, pi. Immediately I know my highest point is pi by 2, right? This is n equals 1. When I have n equals 2, so I have 0, 2 pi. Now this is pi. So I'm going to have 2 now. I'm going to have pi by 2. That's my highest point. And my lowest point is minus pi by 2. Nope, not minus pi by 2. It is minus 3 pi by 2. Minus 3 pi upon 2. Right? And so you keep on doing. So if you have 3 waves, you're going to do 3 waves. And then you're going to have 3 peak and throw. So you're going to have 2 peaks, 1 throw. So on 2 waves, you're going to have 1 peak, 1 throw. On 1 wave, you're going to have 1 peak. And so the more oscillations you have, the larger the curvature. So which means larger of those curve waves, meaning larger the kinetic energy, meaning larger the total energy. Right? Moving on. Nodes. So a node means psi is equal to 0. Oh God. So node means Did I lose all? No, I didn't, right? So node means psi is equal to 0 inside the wall. Now, I have node means the psi equals 0 inside the wall. Node means psi equals 0. And for n waves, I'm going to have n minus 1 nodes. For n waves, I'm going to have n minus 1 nodes. If I have one wave, I have no nodes. If I have two waves, I'll always have one node. Where is the node here? There. If I have n equals 3, I'm going to have two nodes. Where if we draw that one, so 1, 2, 3, these are your two nodes, right? And so on and so on and so forth. So n waves, n minus 1 nodes. Cool. Then we have orthonormality. So psi of m, both of them are x. So psi m of x, psi n of x dx is a dimensionless variable of m and n. And if m is not equal to n, then this is what call orthogonal, meaning it's going to be 0. Now, if m is equal to n, this is normalized. This will mean that your psi is equal to 1. Now, how can any wave function this time can be expanded? Because we have um, so we have the wave numbers, we have the number of waves. So obviously we have the the amplitude, that's the constant there. So and this root of 2 by a, because there is a constant, we're going to consider it c of n. And psi of n indicates psi of 1, psi of 2, psi of 3, psi of 4, psi of 5. You can find the nodes, right? So we can write, so our general equation now, so we found the space equation. The general equation for Schrodinger wave equation, we're going to have psi of x and t is equal to c of n psi of n e to the power minus iota et divided by h bar. Yeah. So that is my wave function. Now, why didn't I write root of 2 by a here? Why didn't I write root of 2 by a? Because you're not always going to get root of 2 by a. You're always going to get an amplitude based on the equation that is given to you. Based on the question that is given to you, you are going to get that. Because it's not always going to be root of 2 by a. The only reason I got root of 2 by a is because I did the equation that gave me root of 2 by a. You're not always going to have root of 2 by a, right? So this marks the end of section 2.3, 2.2 actually. 2.3 and 2.4, we are going to do Fourier expansion. So that is also important. So there is Fourier expansion and then conversion from space to momentum, momentum to space.